11:50. Okay, this is what we are starting now. So let us see. So we have seen now how composite walls in series are there, what how the behavior is. Now in case these composite walls are actually in parallel, what do you mean by composite walls in parallel? Let us see. Okay, in case composite walls are in parallel, what do you mean by composite walls in parallel? Let us see. So composite walls in parallel. Composite walls in parallel. Okay, let us see how to do it. Okay, if the composite walls are in parallel, what happens is you have one wall here, okay, with one K1, and there is another wall here with some other K2, different conductivity. And this side temperature is T1, and the heat transfer happens from here to here T. Now the Q which is going gets actually distributed into two sides. This Q1 plus Q. So what happens? Q is actually Q1 plus Q. There the heat transfer, the heat which was going through this part has to go through this, has to go through this. But here, heat transfer from this side to this side, the total heat transfer Q is equal to heat transfer or heat flux from each of the cases. Make sense? So if that is the case, then what will happen? You will have this is like in series. This is similar to having things in, so not series, in parallel. It is similar to having this one in parallel. So you'll have here T1, here you'll have T2, and you have R1 is equal to L, length which is constant. That time area was constant, now length is constant, divided by K1, K1, and R2 being L divided by K2, K2. Make sense? This is how the things are. So what is Q? Q is nothing but delta T, which is the same for both of them. Delta T is same, divided by R overall, or we can write R. Let us say R. Delta T by R is equal to delta T by R1 plus delta T by R2, or 1 by R is equal to 1 by R1 plus 1 by R2. Very important. Okay. Or R is equal to R1 R2 divided by R1 plus R2. Makes sense? Plus, very good. Where R1 is equal to L by K1A and R2 is equal to L by K2, K2 is K1. Makes sense? Here I want to correct this. This is not capital Q, but a small q. Sorry, not small q, but a capital Q. I'm very sorry. The heat transfer rate. Change that, students. I'm wrong there.
Output temperature over.
No, we are maintaining it. We are maintaining it's a steady state.
Thickness are different.
Materials may be different, but we are maintaining that. See, this side one furnace is there, there's another furnace there. What's the heat transfer rate? There might be a C here. Okay, these are there are cases later on we will see where it has a particular specific heat. Okay, so certain heat capacity is there. That time the temperature is reducing. So those things we are not worried. We are saying this is maintained at T1. This is maintained at T2 due to various reasons. It should not know. See, these are simplifications. We need simplifications to understand this. Always science is first you simplify things. Right? If you don't simplify, then things will go bad. Is it not? You cannot understand. First, understand the simplest case. Slow and steady add the complications. Correct? That's the way we are going. Just like Shivaji eating the porridge. Start from the corner. When you eat a hot porridge, start from the corner. Don't put your hand in between. You'll never be able to eat. Done. Chala. Now, next part. Done, no? Everybody has written this? Okay. Now, what will happen here is, okay, in case we have continuous, like if we suppose instead of this, we have, say, the total qk I can write here, okay? So qk, I will write it as qk. It's better we write qk. We'll write it as qk, right? So qk, because conduction we are talking about. It is through conduction, okay? So now, what is the total heat which is transferred? Now, if you want to calculate what is the total heat being transferred, Qk would be equal to Q1 plus Q2, which is equal to T1 minus T2. Observe that T1 minus T2. It's not delta T. I'm very sorry here. I think I made the delta T. This is proper because delta T will go with minus. So delta T with a minus is okay, but actually it is not delta T. It's minus delta T. Observe that. Minus delta T. It's not delta T. It holds good here because minus cancels all everywhere. But otherwise it has to be minus delta T. So here when I put this one, the Q which is transferred goes with T1 to T2 divided by, I'll write this, this is equal to minus delta T into R1 minus delta T divided by R2, which goes as T1 minus T2 divided by L L by K1 A1 plus T1 minus T2 divided by L divided by K2 A2. Make sense? Or yeah, that is how it is. Okay, you can write that. Okay, so this is the total QT. Write this down. Now we are introducing complications here. Okay, if this was the composite walls, then for the composite wall shown in the figure, or the composite wall shown in the figure, the overall resistance is R R is equal to R1 plus we will have R2 R3 divided by R2 plus R3 plus R4. Makes sense? These kind of corrections you need to make. Now there are number of I will not put the numbers. Wait a minute, students. 9 is over. Put this as 10, students. Put this as 10, and put this as this is okay. This is understood. So put this as 11. 10 is this one. R is equal. This is this. Now let us see some kind of questions which are there. Okay, the questions are important. These are the types of questions which have appeared in GATE. Okay, so I'm having from my memory, I'm telling you which kind of questions may come. You can solve the GATE problems later on. Okay, but I'll give you some typical questions which has come. Okay, typical, not the actual one, the typical. Okay. Say in case I have say example one, example one. I'm going to go with this problem, and then I'm going to extend this problem in example two, example three, like that. Okay, so example one. Okay, determine the heat transfer rate through a composite wall composite wall shown in the figure shown in the figure made of made of walls of silver. Say K is equal to 400 410, copper copper with K is equal to 390, and steel with K is equal to 35. Okay, this I have to name the thing, right? 35 watt per meter Kelvin. This is also right. This one, sir, students. Watt per meter Kelvin. Watt per meter Kelvin. Here also 35 watt per meter Kelvin. Okay. The temperature on one side of wall is 400 degrees centigrade, while on the other is 20 degrees centigrade. So I'll write the wall. This is the wall. Okay, this is the wall. Okay. So here let me say this is silver, which is silver. Okay, which has silver is costly, is it not? No, silver is costly, so we'll put in between. Okay. So here it takes more material. So I'll say this is 4 centimeter, 4 centimeter thick. Say steel wall. Okay. Then we will have the silver wall. Okay, here we'll have silver wall. Then the copper wall, silver of say 2 centimeter, and then 2 centimeter of copper. Okay, so steel, silver, copper. Fine. And this area area is 100 centimeters square. 100 centimeters square. The area is 100 centimeters square. The area is 100 centimeters. Here it is 400 degrees centigrade, and here it is 20 degrees centigrade. Right? So what is the determine heat transfer. That's the first one. So solution Q R overall R is equal to R1 plus R2 plus R1 plus R2 plus R3, which is given R1 is given as L1 by K1 into A plus L2 by K2 into A plus L3 by K3 into A. L1 is given as 4 centimeters, so 0.04. K1 is given as steel, so 35 into area is 100 centimeter square. For 100 centimeter square, you convert it into meter square. How do you do that? 0.01, is it not? It is 0.01. Correct? 10 power minus 4, right? Plus L2 is given as 0.02 divided by K2 is which is made out of silver, 410 into 0.01 plus you will have 0.02 divided by 390 into 0.01. Correct. So together, what is the answer you get? You say it is 100 into, you can get the things together. So what will happen here? So if you use a calculator, you will get 0.04 divided by 35. So it is 0.11, 0.0114. Okay. So 0.00, right? 0.00114, 0.00114, 11428 plus. Here you will have 0.02 divided by 4. Tell me what is the total answer, student. That's we will see the R which is there here. We will tell the total answer. Tell the total answer, students. What will get the answers?
One two four.
Point
One two four.
4. What is the unit? Kelvin per Kelvin per watt. Meter is not there. Watt per Kelvin or Kelvin per watt?
Kelvin per watt meter. Kelvin per watt.
Kelvin per watt meter? No, let us see.
What per meter Kelvin into meter divided by area. Meter square.
So what?
Per watt meter. Area. Meter.
Yes, so it is watt per meter, right? Sorry, watt, Kelvin per watt. Correct. So it is so many Kelvin per watt. Kelvin per watt. Correct. Okay. So if it is so many Kelvin per watt is the this one. So what we have to write next? We have to write Q. Q is delta T by R, right? Q is given as minus delta T by R, which is equal to 400 minus 20 divided by 0.1243. What is the answer you get? We have converted already into Kelvin because the difference is same. Whether it's degree or Kelvin, it is the same. Difference we are talking about. What is it? 3.057. 3. 3.057 kilowatt is the heat transfer rate. Okay? It is a now. Next question. I hope you have written this down. Now the next point is you have to determine the temperature at the interface between steel and silver. That is the next point we will do. Okay. Now example 2. Example 2. Determine determine the temperature at the interface of steel and silver. Hope you can do that. How do you do that? Solution. I hope you're getting it, student. Solution. Okay. R1 is equal to R1, which is equal to R steel, is equal to L steel divided by K steel into A steel, is it not? L steel is what? L steel is 4 centimeter. So you say 0.01 or 4 centimeter, 0.04 divided by K steel, which is 35, into A steel. What is the area? 0.01. So you get a resistance of the steel, right? Once you get the resistance of steel, you know Q. Anyhow, Q is the same. Q is equal to 3.057 kilowatt. Correct. Now, if Q is that, so Q is equal to delta T 1 or delta T at steel and silver interface between steel and silver, or with the steel delta T on steel side only. Okay, divided by, you have the um, delta T on the steel side divided by R steel or R1, whatever you get. So you get T 2 or T1 minus T steel interface divided by R1. Q is known, so you can write the TS. TS is equal to Q into R1 minus, or you can write TS is equal to, this comes there. Okay, so T1 minus Q into R1. You'll get it. So T1 is 400 degrees centigrade minus, you have Q, which is given as 3.057, into what is R1, you have to find. R1 is 4 by 35, right? You can write 4 by 35. Correct? What is the answer you got? 50.6. You see, there's a maximum temperature difference. T1 is 400, there it is coming 50.6. Understood that? So, what does that mean? It means that whenever there is low thermal conductivity, the temperature difference is more. When the thermal conductivity is more, the temperature gradient for the same uh, 50.6 degrees centigrade. Temperature difference for the same heat transfer is higher. This understanding has to be there. These kind of questions have appeared, and these are easy ones. Appears a lot. That is fantastic, is it not? The one which is easy and it appears a lot is a fantastic thing to happen, is it not? These are some of the topics which we have to do, even if it is in the final 1 month. If a person is preparing, then these are the topics we will do. So high priority. Done. Done. Now next, in example two, in example two, determine. This is example three, or in the example one. This is example three. Example three. Example three. Determine. Determine the determine the determine the temperature at the silver copper interface in example 1. In example, determine the temperature silver copper interface. What's the answer? 35.7. You understand the difference? Okay, so the answer is 35.7. Answer 35.7 degrees centigrade. Did everybody get this? Yes. Because practice is important. Next example 4. So this is K1 A1, K2 or K1. Okay, this is K2, this is K3, and this is K4. Or let us put it like this: 1, 2, 3, 4. Let me put 1, 2, 3, 4. 1, 2, 3, 4. Okay. In the figure shown, in the figure shown, okay, the area 1 is for 1. Okay, K1 is equal to K1 is equal to say 300 watt per meter Kelvin. Area is equal to 0.01 meter square. Okay, and L1 is equal to 30 centimeter. 2 K2 is equal to K2 is equal to 20 watt per meter Kelvin. A2 is equal to 0.005 meter square, and L2 is equal to say 15 centimeter. Okay, and then third one, K3 is equal to uh, let's say 150 watt per meter Kelvin. Watt per meter Kelvin. A2 is equal to, or A3 is equal to A2. L3 is equal to L2. And fourth, okay, K1 is equal to K4. A1 is equal to A3. A4 is equal to A1 or K4 is equal to K1, and then L1 is L4 is equal to L1. Determine determine the if temperature on side of 1, if temperature on the side of 1 is 200 degrees centigrade, and on the side of on the you can say this is 200 degrees centigrade and this is 20 degrees centigrade. Okay, on the side of 1, on which side? On the left side. On the left side of 1 is 200 degrees centigrade, and on the right side of 2 is 20 degrees centigrade. Here it's important, determine the total heat transfer and the ratio, very important, and the I'll write it over here, students. It's continued, and the star continues here, and the ratio of heat transfer heat transfer rates between slab slab 2 to slab 3, that is q dot 2 divided by q dot 3.
The right side of that's 4.
Right side is 20 degrees. Right side of 4. I'm sorry. Right side of 4. I'm very sorry. Right side of 4, not 2. I'm sorry. Right side of 4 is 20 degrees. So what is the total R you get? The total R, we get it as R1 plus R2 R3 divided by R2 plus R3 plus R4. Is it not? What is R1? It is L1 by K1 A1. L1 is given as zero point 0 centimeter, point 3. Is it not? So it is 0.3 divided by K1 is given as 300. Is it not? 300 into 0.01. See what is the answer? R2 is equal to 0.15, right? 15 centimeter, right? Yeah, 0.15 divided by K1 which is equal to 20, right? K1 which is equal to 20, or K2 which is equal to 20. K2 is 20 into 0.005, and then R3 is equal to 0.15 divided by, we have 150 into 0.005, then R4 is equal to, we will have this here as zero point 0.3 is equal to R1, right? There's no problem. Everything else is the same, is it not? So what is R1? R1 we get it as, here we get 3, right? 3 divided by 300. 3 divided by 300 is 0.01, correct? Sorry, 3 divided by 300. How do we get that? 0.01, yeah, 3, point 0.1, is it not? You get 3 here, you get this as 303, 0.3 divided by this. So you get zero point 0.1 here also. Correct or no? You get zero point 0.1, right? Kelvin per watt. And this how much you get, you tell me, students. Let me also do the calculation along with you. So when you do the calculation, go slow. As practice increases, you will get the speed. Okay. So if you have this 0.15, and use gate calculator always, students. 0.005, 1.5 Kelvin per watt. The other one is 0.15 divided by 0.005, answer, divided by 150. So you get it as zero point 0.2 Kelvin per watt, and this is equal to zero point 0.1 Kelvin per watt. Makes sense? So we get R is equal to R1, which is zero point 0.1 into 2, plus R2 is 1.5 into zero point 0.2 divided by 1.7, correct? So you get zero point 0.2, so we get this as zero point 0.2 plus, bracket open, 1.5 into zero point 0.2 divided by 1.7, bracket closed, answer is equal to 0.3764, right? What is Q? Q is equal to delta minus delta T divided by R. Delta T is on the other side 200, so 200 minus 20 divided by 0.3764, which gives us as 180 divided by 0.3764, which is equal to 478.21 watts. Okay, you get that? So once that is done, now how do we get the ratio? So you see the Q is equal to Q2 plus Q3. Q is equal to Q2 plus Q3. Now, one of the things, can we do this way? Okay? The ratio aspect. Assuming, here assumption is important. Assuming, assuming the delta T between 2, slab 2 and 3, which may not be the same always, slab 2 and slab 3 to be the same, then what happens? Q, which is equal to 478.21, is equal to delta T. What is the delta T? Do we know the delta T? No, we don't know the delta T. Huh? T2 and T3. Now, yes, so let us find out T2 and T3 first. Okay. So let us see T2. What is T2? Yeah, that should be the same everywhere, right? So T2 is equal to, so T2 here I will say, this I will say, this is T2, and let us say this is T4. Okay, so this is T1. Okay, let us say T3, let us write T3, and let us say this is T4. Fine. So can you calculate T2 and T3? Find that out, then you can do it fast. So T2 is equal to, find out T2, what we'll do, we will say, oh, this is not required, assuming delta T to be same. Okay, that's understood. Okay, Q2 plus Q3. First, let us find out. So this is equal to T2 minus T1, or T1 minus T2 divided by R2. Sorry, R1. This can be T3 minus T4, right? T3 minus T4 divided by R4. Correct? Or we have to take the together things. This is okay. Final answer, what you say, I have framed the question now. So, so it's not like the gate question which is thought about. The question is impromptu. Understand? So just like that, whatever has come in my mind, I'm doing it. These kind of questions will come. Right? So what is T2? So Q is equal to Q, which is equal to 478.21. T1 minus T2 by R1. Okay. Oh, this is not the case. This is not the case. Okay. I'm very sorry. This is not the way. This is not the way. This is not the way. Ah, yeah, yeah. Individually also we can write. I'm very sorry. T2. Oh, this is wrong. 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 Okay. The denominator was wrong. Don't copy it just like that. Denominator was wrong. This would be T2 minus T1, or T1 minus T2 divided by R2, plus you will have T4 minus T3 divided by R. Sorry, same thing. Oh, no, 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 no. This is T3 minus T2, T3 minus T2 divided by R3. T2 minus T3. We want Q2 by Q3, right? So we need not find this one. So Q2 is T2 minus T3 divided by R2, and Q3 is equal to T. No, it is not. R changes. R R3. So what will happen? This becomes just the ratio. So you don't need not calculate again all those things. So what you can write, Q2 by Q3 is equal to R3 by R2. R3 is given as 0.2 and R2 is given as 1.5. That is it. It's direct question. The ratio will give. Simple. So what is the answer you get? 0.2 by 1.5 is zero point 0.1. Okay. Simple. This is the type of questions which will come in GATE. Easy, so you should not miss it. Then next. Next, let us see heat conduction through a cylinder. Okay. Since it comes a lot, all these things, we will do some more practice on this. And we will tomorrow we will go with more gate questions so that we'll get the answers properly.
temperature drop in both 2 and 3 degrees.
That's what you assume. It has to be the same, does it not? And it is the same, that's what we assume. Okay. So, next one. Uh, Heat conduction through a cylinder. Very important, students. Heat conduction through a cylinder. Heat conduction through. See, in general, when you consider the heat transfer, okay, so if you consider, say, take a cylinder, a hollow cylinder that is hollow, okay, and uh, wait a minute. Okay, the cylinder which is hollow. Let us look at here like this. This is cylinder. It is okay, and here the temperature is T1. Whatever the temperature T1. Outside the temperature is T2, and this is the cylinder. Okay. Cylinder that. Okay. So now, if that is a cylinder, okay, here, let us take. See, this is very important because the area changes. T1 and T2 are the temperature. Okay. Now, what is the heat transfer here? If you want to see, heat transfer we take in terms of area, is it not? What do we take? We take Q is equal to minus of K A into dt by dr. But A does not remain constant. That is the problem. If it was a slab, it was easy for us to calculate. But here A does not remain constant. A keeps on changing. Inside the A is different. As you go outside, the cross-sectional area is different. Cross-section of area, which one? This is the area we are taking, you see. This area is what we are taking. This is the area. Initially, the heat transfer is like this. The area is perpendicular to that. That area you have to take. So what we will take? So here integration helps. So let us take a small thing here, small, infinitesimally small strip here, where the area variation is less. So let us take from the center at a distance r of a radius dr, thickness of dr. Okay. So the heat transfer through the elemental thin cylinder of thickness dr as shown in the figure as shown in the figure is as shown in the figure is what can be written as qk is equal to minus k into area into dt by dr, which is actually equal to minus 2 minus k into 2 pi r into L. So see, this is the length L, 2 pi k r into L into dt by dr. Correct. dt by dr. So I can say that, so I can say integration of along dt is equal to integration along minus of qk divided by 2 pi k l into dr by r. So when you integrate, I will integrate from t1 to t2, and here I will integrate from r1 to r2. Make sense? Everywhere integration is used. Write this one, understand. I'll go slow. There is no urgency. Understanding is important. So, how about me taking class from 6 to 7 every day? 7 to 8 is Thursday classes, is it not? Heat transfer. No, no, no. Fine. 6 to 8. 6 to 7. What happened? Evening 6. Not morning, right? Come on. I'm a human. You may be young and you may have the Josh. I'm old already. Huh? No, no, no. 6 to 7 in the evening. Come on. I'm realistic. It's realistic. Because till 5:30, 5:15 or 5:30, we have class for civil engineering. After that 1 hour of class, I will take on heat transfer. Let us complete heat transfer soon. From today only it will start. Today, 6 to 7. 7 o'clock, Murli sir will start class. Why the break? 15 minutes break. 15 minutes break. Channel close is till 5:15. Okay. Okay. So we'll start with 5:45 to 6:45. Every day 5:45 to 6:45 will have this, so that we could complete the syllabus fast. Okay. Correct. No. Just got a mind. That gap is too much. Done. Okay. Now let us go for integration. So students today, but what about our Nishchal? Nishchal will face difficulty, is it not? Nishchal will face difficulty because he misses the continuity. So we will do one thing. We will start a new topic. Which topic can we start? Shall we start with complex numbers then? That would be fine, is it not? Yes. So we will start with complex numbers from 6 to. Is it so?
per day, but if you take three subjects, if you continue that only, you'll be in the track.
Then I'll do one thing. I will start with radiation in the evening. How about that?
So, per day, 3 days you can do it with just one. Complex computing, just
Yeah.
mathematics.
Mathematics. It's not, you will not feel much difficult. We'll go with complex number. This to include Nishchal because it has to have a continuity. We will start with complex numbers today. Yeah. What are the other topics which are
Or you
remaining?
can start that OR and all that.
Yeah, we'll start with industrial engineering. Okay. Don't want mathematics will complete. We'll complete with complex numbers. Okay. So today class 5:45 to 6:45 we will have complex numbers. So and this will continue. Okay. So as fast as possible as we complete, we will be in a very comfortable situation. Correct. You have anyhow break from 4 o'clock till around 5, not 4 o'clock, 3:45 to 5:30. You'll have to. Okay. Chalo, done. 5:45, right? 3:45 to 5:45, 3 hours. 3, 4, 5 hours, 2 hours. It's okay. Fine. That time you can chill out a bit. Or you can learn, of course. Chill out after an hour, I know. So this is done. Okay. So now when you integrate, you get T2 minus T1 is equal to, you are integrating from T2 to T1. You understand the T2 to T1. So it is T2 to T1. T2 minus T1 is equal to minus of Qk divided by 2 pi Kl into log of R2 by R1. Makes sense? That when you integrate all the q's, so Qk can be equal to 2 pi Kl into T1 minus T2. You see that minus is being eaten up by this T1 and T2 divided by log of R2 by R. Correct? Let this be equation number. Where did we come here? Last equation number was 11. So let us go with 12. So let this be equation number 12. Makes sense? Very important. Okay. Now this equation 12 can also be written as, so equation 12 can also be written as, oh, are we, have we muted down those students here? Of course. What about online students? You are okay with it, no? Your afternoon class, evening class at 5:45 to, yes, no?
Yes, sir.
We'll start with complex numbers then. Okay. So equation 12 can also be written as, equation 12 can also be written as Qk is equal to, we could write 2 pi into R2 minus R1 divided by R2 minus R1 into L, we are adding an extra L into K, no, not extra L, L is already there, and we have T1 minus T2, and then here in log, we will write log of 2 pi R2L divided by 2 pi R1L. Now this together comes as equal to K into, here you see 2 pi L into R2 is A2 minus A1, A2 minus A1 divided by, here you see R2 minus R1 into, this K is there, okay, into T1 minus T2 divided by log of A2 by A1, or Qk can be written as K into A2 minus A1 divided by log of A2 by A1 into T1 minus T2 divided by R2 minus R. This further I will write in the next slide. So this is part of the first chapter where we say the basic conduction, convection, radiation we add is introduced. Next we will go with depth conduction, depth convection, depth radiation. Then heat exchanger design. So there it completes. So complex numbers, I think 2 weeks we'll complete complex numbers. There one thing is done. And don't have to worry about remembering and all those things. Sit in the class and look at the pages whenever you get time. Go back, see more than done. But concentrate on these three things: maths, fluid mechanics, statistics. Concentrate strongly on that. You have to get all the concepts in that. Other things, whichever you feel, one subject. You say manufacturing is interesting for you, do manufacturing. You have design is interesting for you, do design. Heat transfer or thermal engineering is important for you, do another one. Select one of those. So like that. First three things: maths, uh, strength of materials, fluid mechanics, have to be strong. There's no options in that, because that being strong helps other subjects. Okay, if you're strong in these three subjects, there's no option. I'm not giving you option there. Okay, I'm saying this has to be done. I'll repeat again: maths, strength of materials, fluid mechanics has to be done. Then you have to take one subject which is interesting. After you complete that subject, go to the next subject. Make sense? Sure. Now another point. So this can be written as, so Qk can be written as equal to K into A of log mean ALM into T2 minus, or T1 minus T2 into X of the wall, where this you can write this is equation number 13. This is equation number 13, where ALM, A log mean, is equal to A2 minus A1 divided by log of A2 by A1, which is log mean area. Log mean area. And XW is equal to R2 minus R1. R2 minus R. Here A1 is inside surface area of the cylinder, and A2 is the outside surface area of the cylinder. Outside surface area of the cylinder. Makes sense? Huh? And here, and here, if you consider resistance to conduction, thermal resistance offered Rk is equal to T2 minus T1 divided by Qk, which is equal to Xw divided by K into A log me. This is important equation which can be given as equation number 6. Question number, and yeah, there are few more things which we will do in the next class. Rest in the next class. Rest in next class. The rest of the portion. Otherwise, if you sleep in the next class, then I'll be in trouble. So next class, rest of the portion in the next class. So you have to be very careful in framing. Okay, so 2 o'clock we'll meet students.